Well, you should be seeing my screen now. This is Rodney Wolfenbarger. I serve as director of the Lifelong Learning Institute at James Madison University. I want to thank everyone for joining us today for the second Zoomtime Knowledge presentation of this week. We had one yesterday that's now available and archived on our website. If you've missed any of the presentations we've done so far, since we transitioned to online learning, those are all available at our website at www.jmu.edu/LLI. I will put that link in the chat window once I introduce our speaker today. Today's presentation is titled The Northern Lights, Mankind's Earliest Impression of the Polar Regions. We're joined by our special guest presenter, Dr. Ralph Allen. Some of you would have taken classes with Dr. Allen, either at UVA or here at JMU as part of our lifelong learning program. He's Professor Emeritus at UVA, a retired faculty member there where he served as Professor of Chemistry, Environmental Science, and Public Health Science. He's also previously served as the Associate Vice President for Research at UVA. At this point, I'm going to turn it over to Ralph. Ralph will be able to begin sharing his presentation. If you need any assistance with your technology, you can't see or hear Ralph, or you're not hearing me, just send a private message to either me or Sue G. Sue is our program assistant. She's connected, serving as host of today's meeting. We'll try to help you remotely. Otherwise, I'm going to mute myself. Ralph, welcome, and thank you for volunteering your time today.
Thank you all for joining. All I have is a frozen screen with just Rodney.
Ralph, we have you coming through here on our end, or I do, and I can see you. Are you having some difficulty getting with screen sharing because of your frozen screen?
Well, I don't think so. So I can go ahead and I'll start that.
All right, thank you. And I'll stand by if you need any assistance.
All right. Well, if you can all hear me, technology sometime. So, about the Northern Lights, I was going to ask, how many of you have seen the Northern Lights? Just raise your hand. Well, there's a few of you that have. Anyway, it's something that you don't see very much, particularly if you're in the South. And we'll talk a little bit more later on about why it is that only people in the northern regions, and the further north you are, the more likely you're going to be able to see the Northern Lights. But we do see the sun every day, and well, not every day. Today we didn't see the sun, but when we see the sun come up, you sort of think about people that were in the past, isolated the way we were, but they didn't have lights at night. They didn't have things in the day. They probably paid far more attention to the skies and what was happening to the sun and the moon and everything than we do today. We know and expect the sun to come up. But when people saw the sun come up and saw these beautiful sunrises, they thought about what caused those. Now, to the ancient Greeks, they believed that the sun was Helios and the moon was Selene. These were Greek gods and goddesses. Now, Aurora was a sister to these gods, and every morning she would get in her chariot and with the multicolored chariot fly across the sky, alerting her siblings to the fact that a new day had dawned. And so people tried to explain what it was that they saw in nature every day, and they often resorted to it being the gods that were somehow involved in the whole thing. So they also noticed things like days getting shorter and shorter, and the growing season ended. And the fear that maybe it would just be night all the time, and particularly if you lived in the north, where during the winter time, the nights were much, much longer than they were during the summer. So people began to devise ways of looking at or thinking about what it was that was going on, and understood that once the sun reached a certain point, it began to come back again, and that they knew that summer and spring and the ability to raise crops again was coming by. And so the winter solstice was something that was celebrated. You have a place like Stonehenge that was set up to presumably help people understand when it became midwinter and when the longer days were over. The ancient Roman god celebrated it as well, Saturnalia, which probably was why we have Christmas in December. Was dedicated to the god Saturn, who was the god of agriculture and to time. So people saw these things in the past and understood that what was going on in the sky was going to be in a somewhat predictable way, and you could expect changes to occur. So even in the Far East, which we in the West don't know very much about, but in Japan and China and in Asia, people also recognize that the days got shorter, and then at a certain point, midwinter, then the sun goddess came back out again, and they were able to see that returning. Now the question was, what did they think when they saw this? Now, clearly, these are time-lapse photographs, because if you try to take pictures of the northern lights, experiencing the things, most of them have seen in the dark of the night. They really are these vivid colors of what's going on. But you can see that from the fact that the stars are moving, that these are in fact time-lapse photographs. And the northern lights occur in all sorts of different colors, all sorts of different patterns. And so the question is, when you saw these, what did you imagine they were? Because you didn't see them very often. But when you did, it must mean something pretty spectacular was going to happen. Well, we eventually call these northern lights aurora. Remember, that was the goddess who brought sunrise, so it looked like a sunrise, but it didn't occur like normal sunrise. It looked like the wind was blowing, and so we call it aurora borealis. And I've heard it described in two ways, that boreas also meant wind or north wind. And so it was fairly clear to people that when these things occurred, it was something rather unique and special. And it occurred to people the further north you lived, the more likely you were to ever see these things. But the Greeks saw them. It's fairly hard to try to interpret these things, that even in the Stone Age, when people were carving patterns and things in these caves, 30,000 BC. The picture on the left, it doesn't look like very much, but archaeologists interpret that as being, that's what they saw in the sky, this random sort of behavior of things. Likewise, some of the things that show up in cave paintings were this stick man. And the stick man is also thought to perhaps be evidence of something that was going on in the sky, in this movement of men or something in the sky. People didn't really understand what these things were, but they did notice them, and they were quite a unique thing. Documentation of the Northern Lights in cultures, particularly in Eastern Asia, go back to about 4,000 years ago. And so this is documentation where people actually wrote down a description of what they saw. And they also interpreted what they saw. If you look at this particular image, you might recognize where the idea of a dragon might have come from. So people in the latitudes that were far enough north could see the aurora more frequently than people that lived further to the south. And so the aurora only occurred maybe once or twice in their lifetime. And so it was something very special and something that was quite unique, and it must mean something to them. Well, here's a written document that goes back to 2600 BC. It tells the story of Fu Pao. She was the mother of the Yellow Emperor. Now, Yellow Emperor is one of those legendary Chinese sovereigns or cultural heroes that if you ever study Taoism, you'll find this is one of the early figures that talks about this way in which humankind ought to behave along with nature. So this was the story of the mother of the Yellow Emperor. And the important thing about that was that she became pregnant at the time that this display of lights occurred in the north. Fu Pao saw strong lightning moving around the star Su, which belongs to the constellation Bai Dao, and the light illuminated the whole area. Now, of course, the interpretation of that, stars were obviously visible. They knew what direction they were looking, and those stars are in the north, so they were looking in the north, and they saw a bright light. It was light enough to illuminate the landscape. And lightning is a term that was often used in trying to describe these polar lights that people saw, particularly in the old written descriptions. It was the closest thing they had to sort of describing what it was that went on. So this was a very special birth that occurred in China, and it was documented as this was a very special occurrence. It was marked by the visibility of the northern lights. 593 BC, the Greeks documented a series of times in which they saw the accumulation of moving and burning clouds as they described them. Now, since it only occurred a few times a decade, once you got to the horizon far to be in Greece, it was perhaps something that people didn't see very often, and it pertained to something very special that was going on. Now remember, the Greeks believed in all sorts of things like being able to divine what was going to happen in the future. And so seeing these things clearly said to them something special was going to happen. Plutarch describes the northern lights in his writings, said during the days there was an enormous and furious figure in the sky. Well, again, most people in this early Greek period saw these as some kind of special, ominous kind of thing, pretending to something. It was like a flaming cloud, which did not stay in its position, but moved windingly and regularly, so that the glowing fragments were in all directions, and fire was blazing as the comets do. Those fragments came loose during rushing and unexpected movements. And so people that watch the northern lights can see in that description exactly what it was Plutarch was describing. Now, they have seen the lights only a few times during their lifetime, and during that, now we know something about the origin of these things, and we understand that it took some incredibly strong solar activity for sightings to be as common as they were, so that the Greeks observed them when they did. But that's not what they understood and realized it to be. One Greek philosopher, on the other hand, had something to say that I think pertains to us now as well, but he said, this is Aristotle, he said there are in fact two things, science and opinion. The former begets knowledge and the latter ignorance. We might think about that as we're looking for how we're going to deal with this pandemic that we're looking at. Science is what's going to be important, not just what people think. So Aristotle came up with a theory that he described what he thought went on. Now you have to remember at the time, the Greeks thought that all matter was made out of four materials: earth, wind, fire, and water. And so he saw what was going on was steam that was raising into the clouds, and it hit the fire element, and that ignited it and caused the northern lights. And so Aristotle attempted to explain it based upon the limited amount of knowledge that he had. Now, one of the interesting things that shows up even today in things like the flags of Turkey, for instance, is this event that occurred in 339 BC. Philip of Macedonia, who's probably most known for being the father of Alexander the Great, was going to attack the city of Byzantium. And part of how he was going to do that was tunnel under the walls. But in the middle of the night that the attack was planned, there was a sudden light. And that light was shaped like a crescent moon that illuminated the landscape. Well, in seeing this thing and being able to see the troops lining up to go into this tunnel, this warned the defenders, and it gave away the planned attack. And so this sign, this moon-shaped vision that they saw that displayed the lights, was put onto the coins of ancient Byzantium. So you see on the left here, the coin, often referred to as the star and the crescent. Ancient writers who explained it said that the Byzantines were recognizing it as a tribute to their goddess that saved them from Philip by providing this light to reveal the tunnels. And so the question was this a moon, crescent moon, or was it in fact this arc that they described the northern lights as being in? And the interesting thing to people today, when you see that star and crescent on the Turkish flag and then many other things, it's referred to as the crescent moon. And there's a real question about whether that's true, because in the Middle East, typically the crescent moon is seen in the opposite direction. And so there's some question of whether this is still a commemorative of that display of the northern lights. Now, it shows up in the Old Testament as well. There are several places, but perhaps the best known one is the 6th century BC prophet Ezekiel, who wrote what he saw. A whirlwind came out of the north, a great cloud, and a fire enfolding itself, and a brightness was about it. And out of the midst thereof, as the color of amber, out of the midst of the fire. So this is interpreted again by people that look upon it as sort of, is this some sort of a sign? Did it mean something? Of course it did to these people, but was it in fact a display of these northern lights? Now, the northern lights were rare in Southern Europe, and we know now that they would only have appeared there at times when there was a very intense activity on the sun. But when they did occur, they were much more terrifying than they were to people that were further to the north. And so people in France and Italy believed that these were bad omens. Something bad was going to take place, plague or death. And it said that the skies blazed red just a few weeks prior to the French Revolution. Well, there were a number of other things that people spotted that saw that these were bad omens. So we all remember the Ides of March. 44 BC, the northern lights appeared in the sky about that time, just as Julius Caesar died. So was that warning about the Ides of March? Was it because of the display of the northern lights? It said that the northern lights flamed in the sky of Palestine when Titus destroyed Jerusalem. Now, one of the more interesting observations is that the Roman Empire was destroyed. And at that time, there was nearly 1,000-year-long period that the northern lights were not seen in Italy. 1,000 years, they didn't see them. And that was after the Roman Empire had died. So did these lights have something to do with the importance of Rome? Often, people saw the blood of martyrs. So further north in England, when Thomas Becket died, murder in the cathedral in 1177, the skies were said to be a blood red. More recently, auroras appeared at the time of Pearl Harbor in 1941. Now, one of the things that's sort of more pertinent perhaps to Virginia was that the night after the Battle of Fredericksburg, it was clear that there was an aurora seen that night. It illuminated the field after the battle. Those in the Confederate Army took this as a sign that God was on their side, because rarely in Virginia did you ever see these northern lights. This is a painting by Frederick Edwin Church of the aurora borealis. It was painted at about the time of the Civil War, American Civil War, and it represented the conflict that went on in the Civil War. And so you can see the importance that this aurora had throughout history, as people still didn't really understand where it came from and what went on. So again, let me just show you a globe to sort of remind you of where we are relative to the Arctic Circle, relative to the north. Now, when people began to explore the polar regions, some of the early people were the Vikings and later on the English. And as people went into this region, you began to see things that you really didn't see so frequently in the more populated areas further to the south. But people lived in these northern regions. And while we're on the picture of the globe, let me remind you that if we're trying to look at them from here in Virginia, we are looking around a globe, and what we see is only the very high altitudes that are up at the Arctic Circle. So part of what we're going to see as we describe scientifically why the northern lights look the way they do and why we see them so frequently in the south is that we're looking sort of, and we can't see over the edge of this rounded globe. But we know that the northern lights were familiar to the people that lived in the north. There was mythology and legends that grew up as the indigenous people described these lights. And again, because they were more common, they were typically associated with things that were less catastrophic and some of the Inuit tribes that were seeing these things that lived up in the region at or near the Arctic Circle. Some of these tribes, interestingly, saw these as dead humans playing a ball of game using a walrus skull as a ball. And then, interestingly, other Inuits somewhere near them saw it as walrus spirits playing ball with the skull of some unfortunate human. But again, they saw it as some sort of playful activity that was going on in the sky because they saw it so frequently. In Norse mythology, again, people that lived fairly far to the north and saw them quite commonly, they saw them as lights that were reflecting off the shields of the Valkyrie. These were the warlike women who Odin had picking up the dead from the battlefield and bringing them to Valhalla. Valhalla is where these fallen heroes, these warriors, were going to spend the rest of their time eating and drinking in the halls at Valhalla. Some also thought it was Freya, who was the goddess who was riding on horseback across the sky. Now, to the Vikings, these were fairly common things, and sometimes they had this kind of bridge-like structure, and they interpret that as the sort of glowing arch where the warriors who were killed in battle were led into Valhalla. And so, again, in the further north, these were looked upon as not such rare things, but something that they could relate to in their sort of everyday life. Interesting, in Great Britain, particularly in Scotland and the northern areas, these were seen as dancing men, or the nimble men, the merry dancers. They again saw them as kind of a peaceful sort of thing. Sometimes, particularly when there was red light, they saw that as evidence of battles that had occurred, and that was representing the blood that was shed in the battles. In North America, the Algonquins saw these lights as reflected fires that the Creator had to remind his people that he remembered them. Again, sometimes the myths involved dead warriors or sometimes enemies. Again, further south, because they occurred more or less frequently, they associated them with battles more often. Well, now remember that after the fall of the Roman Empire, there were few references for 1,000 years to anything like the Northern Lights, particularly in more southern Europe. Further to the north, remember that the time of the Vikings was, nearly 1,000 years after the fall of the Roman Empire, and somewhat before where they began to see them. When they did occur, written texts described them as something that was embellished with warlike predictions, and there was some superstition about them because, again, they didn't see them very often. And these are woodcuts that sort of represent images of what they saw these things as being. Now, one of the more realistic descriptions of the Northern Lights occurred in a work written by a Norwegian. It was a book that was prepared for the Norwegian king to sort of explain to him his duties and what was going to happen. Remember, at this point in time, the Norwegians were out and about, traveling across even as far as to North America. And so this book described not only where they had discovered around the world, but because they'd been this far in the north, they understood something more about the lights. And so they described them for the first time as Northern Lights. They recognized this was something that occurred in the north. There were some theories that they put forward at that time that were actually sort of held to for the next 500 years. And so you see, it wasn't until the middle 1700s that people began to seriously try to figure out how to describe what in the world was going on with these lights. So one of the early people that looked at them and described them, it was a rare thing, but Galileo was quite excited that he got to see the Northern Lights. Remember, they were still fairly rare at this period of time, but there was a large display of Northern Lights that occurred in about 1621. Galileo was the first one that used a scientific name, aurora borealis, for describing the Northern Lights. Now, this was a rather large display of lights. And again, people had already begun to associate the fact that you saw Northern Lights at the same time you saw solar activity, namely sunspots. And Galileo was one of those people that had noted the fact that there were sunspots, that there were these little dark places on the face of the sun. So 1621 was a fairly rare occurrence, and Galileo saw it and tried to describe what went on. Again, sunspots had not been observed. About the display occurred, there were sunspots again. So already the sun and these Northern Lights. At the period of time, this was described as the Maunder minimum, and it was a time when the environment of the Earth was kind of messy. We were ending ice ages, things were cooling off again. But anyway, at the end of this period, March 17th, 1716, very dramatically recorded a quite gigantic display of the Northern Lights. And it's interesting that at that point in time, in England, it was a very special day. The people had come back reporting that the Jacobite uprising in Scotland had been put down, and the commanders had brought these prisoners back to London to the king. king agreed to an act of prosecuting the rebels more speedily, in other words, hanging them all. And of course, in Scotland, this was a very ominous bad time, but in England, it was quite a time of excitement. But interestingly, the chroniclers who were writing about what was going on paid less attention to the end of the Jacobite uprising and more to the fact that there was this gigantic aurora display, red. And of course, in Scotland, they saw that as a act that was telling that the gods were unhappy with the fact that the king was going to prosecute and persecute all of these Scots that were involved in the rebellion. One of the people who got up from his dinner table while he was entertaining guests was Sir Edmund Halley. Halley is the English scientist who's best known for the Halley's Comet and predicting, forecasting when it was going to come and how frequently it was going to return. He's quoted as writing, "Auroral displays are due to particles which are affected by the magnetic field. The rays are parallel to Earth's magnetic field, and the vault-like shape is due to a perspective phenomena." In other words, looking sort of over the globe and looking up into the atmosphere. So this was kind of a description that he came up with after being so excited to come out and watch these northern lights, and then trying to figure out what in the world went on. And so his theory was basically that we knew that the Earth had a magnetic field. And in fact, early polar explorers had identified where the North Pole was. And it's not at the point of the geographical North Pole, and it moves. But it is recognized that there was a magnetic field. And Halley said that the solar wind, which must have been some kind of particles that were coming from the sun. Now, this is a period of time when we didn't know that it was electrons and protons and neutrons, but he saw it as some sort of a charged particle that must be coming from the sun. Remember this connection between sunspots and when we saw the northern lights. And it was an interaction with this magnetic field. And so that was really the kind of first scientific finding and attempt to describe what went on with the northern lights. And it still holds true. Now, it's interesting, the other scientists at the time were trying to understand what went on. We all know Benjamin Franklin, and we know about his flying a kite and the key that got electrically charged by flying it up into the cloud, and recognized that lightning was in fact electricity coming down from the sky. So Franklin knew about electricity in the sky, and so he theorized that the lights were caused by electrical charges that had accumulated at the North Pole and were somehow intensified by the snow. And when they became overcharged, he had worked with Leyden jars where you could store electricity, and if you got too much in them, they would arc across. And so he thought this arcing across into the sky was sort of the opposite of the lightning that sort of normally comes down on us. Well, Franklin was right about the northern lights. They are caused by electricity, but not quite in the way that he envisioned them. So in the 18th century, scientists had discovered the connection between the aurora and the disturbances in the Earth's magnetic field and sunspots. And so you had these relationships that were sort of understood, but not really how they in fact function. So let me go back for a moment and talk about maybe an experiment you all did as a kid. You put a bar magnet down, put a piece of paper on it, and sprinkled some iron filings on it. And when you did that, you saw the magnetic lines of force as they lined up going from north to south pole. And so people recognized the fact that a compass pointed to the north, that in fact the Earth was like a giant magnet, and that there would be a magnetic field, much like you saw with a bar magnet. And so people understood that the Earth had a magnetic field. And so then how was it, and what was it that it was interacting with as it came from the sun? Now, to me, it's kind of interesting to see the people that were involved in trying to figure out what was going on with these northern lights, because they show up as scientists who had other contributions as well. We all know about Celsius. Well, we don't know as much as the Europeans and the rest of the world knows because we still use a Fahrenheit scale. But Celsius is the one that developed a scale in the thermometer between 0 and 100, which was boiling and freezing of water. 1741, Celsius sort of theorized and wrote down about the connection between the northern lights and the magnetic activity, that when magnetic needles began to fluctuate and carry on, indicating that something was happening in the Earth's magnetic field, that's the time when you saw northern lights. So that's the second correct scientific finding about the northern lights, 1741. Interestingly, 1790, in Britain, the chemist, and I have to call him a physicist as well at the time, this book was written about him. He's the one who calculated the weight of the Earth. Henry Cavendish estimated almost correctly that the altitude of the northern lights was much higher, much high up into the atmosphere. It was not near the surface of the Earth. And so this was the third thing that was correct in terms of describing what was going on. Another person that was involved with this in 1866 was Angstrom. Angstrom, again, very familiar with the northern lights, but he was also a spectroscopist. He was a person that looked at the light that you see in a spectrum. So we've all seen a rainbow that comes through a prism. What Angstrom did was break that rainbow down into a much bigger span so that he could see essentially individual wavelengths of light. And he discovered that there were certain holes in the spectrum of light. The way we see the sun's light, it looks white, but we know by putting it through a prism that it's all the visible colors. But what Angstrom discovered is that there were certain places where there was light missing or lower intensity. And eventually that was discovered that that was hydrogen and helium absorption on the sun's surface. And that's how we know that the sun is made out of mostly hydrogen and helium and other light elements that we also see reflected by breaking down the spectrum of the sun. What Einstein discovered is that you could use a gas and you could excite the gas and it would emit colored light of a very specific wavelength or color. So if you take sodium and put it in a flame, you get yellow light. If you take potassium and put it in a flame, you get green light. He also, again, had noticed that there were certain lines that were missing because light was absorbed at certain wavelengths. And so Angstrom was figuring out the interaction of light being excited by other light, or as we will see, by being excited by an electrical discharge that occurs in gases. A Finnish scientist a little bit later observed that the aurora zone was a ring. Now, how did he discover this? Well, he was exploring the Arctic, got trapped in the ice above the Arctic Circle, and was able to spend the winter looking directly up at the northern lights instead of across at them, and saw that they were in fact in a ring, and that ring has been confirmed now by observations from space. So it was a Norwegian, Birkeland, in the early part of the 20th century that sort of brought all these theories together, because he suggested that the northern lights were associated with an electrical system, that it was electric currents. It was electrons that were coming from the sun. And when they interacted near the Earth with the magnetic field, they provided acceleration or caused these electrons to be even more energetic as they interacted with the Earth's atmosphere. And so they were accelerated following the Earth's magnetic field lines. And remember, the magnet had at the North and the South Pole, those magnetic field lines all go down toward the North and the South Pole. So in passing, I'll point out there are southern lights as well. The problem is there weren't very many people living down there to see them, and it wasn't really until there was exploration of Antarctica that people began to see the southern lights as well. These lights, this electric field that was generated that Birkeland predicted, there were a lot of people that doubted it, but in the 1970s, satellites in fact showed that that electric field existed and that that was where these aurora originated. So Birkeland's theory, to sort of sum up, was that there were sunspots or things on the solar surface that were behaving, that were shooting very energetic electrons toward the Earth. It was the geomagnetic field of the Earth that deflected most of those electrons around us, but it did focus some of those electrons down toward the polar regions. And it was the interaction of these high energy electrons with the gases in the atmosphere that caused the northern lights. It really wasn't until the end of the 1950s that it was convincingly shown that the particles which excite atoms and molecules are mostly electrons. Up until that point, we understood that the solar wind contained charged particles like hydrogen ions and helium ions, but it's the electrons that turn out to do the real business. Just want to mention a little bit about solar wind. Solar wind is the description of the electrons and the charged particles, again, mostly electrons, but charged particles that are emitted from the surface continually and flow out in all directions around the sun. And they flow toward the Earth. This shows the size of a solar flare compared to the size of the Earth and the scale of the Earth. So these are immense events that occur on the surface of the sun. So there are two kinds of things, solar flares and sunspots. Each of them give rise to a solar wind, mostly electrons, that are accelerated at very high energies, 350 to 400 kilometers per second. Very high energies toward the Earth. So what would happen to the Earth if we didn't have the magnetic field to protect us? Well, if we didn't have the magnetic field to correct us, and it corrects very far out. It's estimated that you can feel the Earth's magnetic field out about 30 Earth radii out into space. And what happens is all these charged particles interact with that magnetic field. And so instead of bombarding the surface of the Earth itself, they sort of sweep around the outsides. Now, why is that important? Well, if that stuff hit the Earth directly, a number of things would happen. First of all, it would have swept the atmosphere away. We wouldn't have an atmosphere. We probably wouldn't have water. All the volatile stuff would have been swept away. Second thing is, if those charged particles get very far close to the Earth, they begin to interfere with things like satellites and radio signals and all those sorts of things. And I'll come back in the end and say why it is that that's important. It also doesn't sweep away the ozone layer. And the ozone layer is what protects us from the harmful ultraviolet radiation that comes from the sun. So the sun, which we appreciate from the fact that we get all this nice light that warms us and grows crops, also has some very damaging properties. The ultraviolet that will do damage to us, and these charged particles that would do even more damage to our atmosphere. So the magnetosphere, this evidence of the Earth's magnetic field, saves us. It goes far out into space, and it diverts most of the solar wind around us. Small numbers of electrons are diverted and follow in toward the poles. Remember those regions that I said the Earth's magnetic field focuses on the North and the South Pole. And so some of those electrons get in, a relatively small portion of them. But the time that they're most likely to get in are the times when there is a lot of solar wind. In other words, when there's solar flare and when there's problems that are going on in the atmosphere. So the electrons spiral down toward the Earth, and when they encounter the atmosphere of the Earth, they have enough energy to cause excitation. And so to sort of sum the whole thing up, energetic particles, a few of which, mostly electrons, are accelerated toward the poles. And if they're accelerated down into the atmosphere, they begin to interact with the atmosphere. So what is the atmosphere mostly? Well, the atmosphere mostly is oxygen and nitrogen. And so those turn out to be the things that we sort of see excited by the electrons. The region where the acceleration occurs is fairly high above the Earth. And again, this was predicted by Cavendish, 620 to 6,000 miles above the surface of the Earth. The particles, the electrons, are accelerated down toward the poles. And once they get to the place where they can begin to interact with gas molecules, the gas molecules in the upper atmosphere are relatively rare. That's why you need oxygen when you go on Mount Everest, that the density of the air gets to be less and less as you go up to the top. One of the things that happens is once these molecules are excited, ionized, excited by these electrons as they're coming down, they get into that excited state, one of two things will happen to them. They'll either emit light, remember like the gas cloud where there's an electrical discharge in it, look at the lightning that you get when there's a thunderstorm. It either emits the light or it runs into something and transfers the energy to another molecule. And so you can imagine as the atmosphere gets denser, as you get closer to the surface of the Earth, the excitation gets lost. It doesn't emit light. It causes other molecules to be excited. So what is it that's excited? We know the atmosphere is mostly oxygen and nitrogen. And so you look at the emission of nitrogen and oxygen, and you see that oxygen has a green line and a couple of red lines. And so what color mostly are the aurora? Excited oxygen, right? The green line and sometimes red line. When you get down to lower atmospheres, you begin to get more nitrogen. And the reason is that nitrogen can get into a state where it can't transfer the energy as quickly. It doesn't emit light as quickly as the oxygen does. And so it will occur in even lower atmospheres. And so that's when we get the blue colors. So to sort of summarize, we look at the fact that there is a sun that is emitting charged particles. Those charged particles hit the Earth all over. Some of them are accelerated toward the poles. And during geomagnetic storms, we see the aurora. We don't see them all the time. We see them at times when there's intense solar activity going on. Again, I told you there were two things: solar flares. Billions of tons of material are emitted. Lots and lots of material coming off of the sun. The other things are the cooler regions, the sunspots. And again, the sunspots also have gusts of particles that are flowing out of those cooler regions into outer space. So both of those kinds of activities cause immense amount of electrons that move toward the Earth. And again, these electrons, as they're accelerated down, excite molecules of gas. The molecules of gas, or the atoms of the gas, will emit light down to a certain point, in which case there's so many other gas molecules that they tend to lose their energy by collisions. And hence, we don't see the aurora going all the way down to the Earth like lightning strikes do. We see it sort of finishing up at about 60 miles above the Earth's surface. And again, Cavendish sort of calculated that, but kind of came close to the notion that it didn't go all the way down to the surface of the Earth. So think again about us trying to look over the curvature of the Earth and looking out and seeing we're only going to see things that occur very high in the atmosphere. As you go further north, you're liable to see the things that occur further down into the atmosphere. So again, the auroras are usually seen at a height of about 300 to 60 miles above the surface of the Earth. The colors we get depend upon the gas and the mixtures of gas. Remember, they're not uniform in their composition. Oxygen is heavier than nitrogen, so there's more nitrogen out further than there is oxygen. So we get these things, these auroral crowns, and you can see them from space. But in fact, if we look at them from down here, if we look at them from Virginia, we're looking at upper atmosphere things, and we're looking through clouds. And so we see these things not because we're seeing something on a flat screen, but something that's three-dimensional, and that's why they look like they're moving so much. Here's from a satellite in space where you can see that aurora. Now, most of them are greenish yellow, but sometimes they're tall. Sometimes the tops are red. On rare occasion, the sunlight hits the top of the thing as the sun is just going down. But again, most of the emission that we see is from nitrogen and oxygen, and that's why they're green and red and blue for the most part. And because each type of atom has colors that are unique, we can in fact tell something about, if we look up at the sky with a spectrometer, we can tell something about what's being emitted by the colors that are showing up in the spectrum. Well, again, it's mostly oxygen. Green radiation prevails at the lower altitudes and red at the higher, where the excited nitrogen molecules are. And at lower atmospheres where we see more blue, where again you have nitrogen showing up. So depends upon the density of the air. It depends upon what's called the radiative lifetime, how long a particular molecule or atom can hold light. So it's rare occasions that we see these deep red colors from top to bottom. And so it's hard to explain sometimes just based upon understanding that it's electrons, exciting gas, being accelerated at our polar regions. Well, I want to just leave you with, if you want to see the northern lights, monitor the Space Weather Prediction Center. There's weather in space. Remember the solar wind? Well, why do we have a National Weather Service predicting space weather? Well, it has nothing to do with whether we're going to see the northern lights. It has to do with interference in our communications. We rely on so much things that are being targeted into space and then back down to Earth. And when there's strong solar storms, those communications can be interfered with, like static electricity, or they can be disabled completely. So that's why we have predictions so that people can take our communications and satellite systems. But it also does tell you times when you're likely to see the northern lights. But the best way to see the northern lights, go in the winter and go north, far north. That's where you're going to see them. So hope you all get to see them at some point in your life, even if you have to do a long cruise up along the Norwegian coast. Okay, let's see if I can get out of this now. Oops.
All right, Ralph, we've got you back. Thanks for stopping your screen sharing. We had disabled video while you were presenting for everyone just because of the issues we had been having with connections, but there were only a few little audio blips, so some people might have some questions about clarification. But in the chat window, we have several questions that I'd like to just read to you and have you respond, and then we will accept other questions beyond these. I think some of the questions you've answered, one of which was, why does green seem to dominate? I think you mentioned that there at the end. I also heard you respond to this question, are there southern lights as well? Are there any differences, Ralph, between the northern and southern lights that you would like to explain or address?
Yeah, the only difference is there's not as many people in the South that get to see things.
Next question said, this is one we got by email actually, that I copied into the chat window. It says, we radio amateurs are suffering from poor shortwave radio propagation conditions nowadays because the sunspot cycle is at a low, so there's less solar radiation to charge the ionosphere. Is this also resulting in fewer northern light displays, Ralph?
Yeah, there is a cyclic period of the sun. Forget about all the sort of normal solar activity, but there seems to be something like an 11-year cycle for the sunspots and so forth for a lot of solar activity. Now, in addition to that, there are these major eruptions which occur sort of without warning, and that's why the warning system is there.
There's another question, Ralph. You had mentioned about, in your last slide, the best place to see northern lights, and you talked about when that would be and where that would be. But this question says, when will we be able to next see the lights from Virginia in our lifetime?
That's probably completely unpredictable. It depends upon an immense amount of solar activity, and it occurs very rarely. As I said, in Greece, there were periods of time when there must have been a great deal of solar activity. The fact that they would be able to see them even a couple of times a decade. But yeah, they're quite unpredictable. And that's why when people take these tours to see the northern lights, as you go north, there's a pretty good chance that you'll see them, but they're certainly not there every night. We spent a year in Norway, and you didn't go out and look for them every night, but and again, we were south far enough, but you see them best in the winter, of course, because it's dark for longer, but they're quite unpredictable, and you just don't see them that often.
Ralph, the next question talks about changing climate and if that has any impact on northern light displays.
I don't know an answer to that, because this is mostly an upper atmosphere kind of thing. I just don't know.
Thank you. Another question here comes from Joel. Said, I recall when I was a kid being told that the lights were ice crystals in the atmosphere being hit by sunlight. Have you ever heard that, or does that seem like a familiar explanation that would have been offered in the past?
Yeah, I think that that probably goes back to the Viking times and even earlier. That's kind of what people thought was going on, that it was something that was being raised up from the snow and everything in the Arctic and the reflection of the sun. That was a prevailing theory at one time. Again, it's been relatively recently that we've really understood these things.
All right, and Ralph, the last question, I will let you still respond to that because we've had a few, and maybe there was an audio glitch when you were explaining, but could you quickly just remind everyone, if they did want to see the northern lights, what's the best place or time that they're more likely to see the display? A lot of questions about Alaska and specific locations.
Yeah, I think that, anywhere in the north that you can get during the winter time is the best way. Now, I mean, I spent a summer in the Arctic, 83 degrees north. I didn't see the northern lights once. I did see the sun 24 hours a day high above me, but so you want to be there in the winter where you're more likely to see them. But again, anywhere in the north. And so places, the further north you get, the more likely you are to see them because you're not looking over the slope of the globe. So Alaska is a good place because there's a population living there. but you do want to sort of get away from all the city lights and things like that. It's sort of like astronomers, you know, they don't like all the glare of the city lights interfering with seeing them. I think we can ask Pat Harkins where's a good place to see them.
And let me go ahead, Ralph, that's a good prompt there. I will, just a second, I'm going to unmute everyone and give them back permission to unmute their own microphone. If you saw me laughing, it was because Joel had mentioned in response to the last question I asked, it said, you say my question goes back to Viking times. I'm old, but not that old. So I'm going to, I've extended permission for people to unmute their own microphone. If anyone has any questions, comments, or feedback for Ralph, you can unmute yourself one at a time and manage those at this point.
Well, Ralph, to respond to your question, we went to Norway in January. It was very cold. It was definitely winter. Not much sunshine or daylight at all, and went up inside the Arctic Circle. And we were fortunate enough on a 10-day trip to see the Northern Lights 3 occasions. So it was a great, that made it a great trip. Thank you for the applause, Sue.
And if there are others, questions, comments, feedback for Ralph, or you're just a friend who's on the call would like to say anything, feel free to turn on your microphone. You can also turn on your video if you wish.
I didn't mean to suggest to Joel that he dated back to the Viking times, but his theory dated back to the Viking times, and that's perhaps because people who told him about the Northern Lights weren't up on the science. Remember what Aristotle said, there's science, there's what you kind of think is going on.
Well, Ralph, I did, go ahead, Pat.
No, I have no question, no question.
Okay. Carol, Thomas, I see your video on. Do you have any comments or questions? Well, I did want to tell everyone, Ralph, while we have people connected, that we've worked out with you as our first wave of online courses that we will be offering your class Finding and Exploring the Polar Regions of the Earth online. And once we have this recording available to us, we will send that out to everyone by email, along with our recording from yesterday's session by Dr. Dana Henry. And along with that email, it will include a registration link and information about Ralph's course. And Ralph, we plan to offer that on Wednesdays from 2:30 until 4 p.m. And the format for that we've decided for our online classes. Generally, we would have 2-hour classes. We thought that's quite a bit of time to be sitting at a computer. So we will be offering that class in 6 90-minute sessions once a week. And again, the details about that course and some others will be coming out, if not tomorrow, this weekend. Ralph, you have any other comments?
And with a break in the 90 minutes, so you get a chance to get up and walk.
Right, right.
Get something to eat. Be sure and bring something for the speaker.
Well, I don't see any other questions here, Ralph, in the chat window, but I want to thank you for your time, your preparation, and just for pushing through today with the weather we're having and the connection issues. It was only slight, but it did occur, and I'm glad that you anticipated that and had a plan for working through it.
Looks like somebody has their hand up.
They're clapping for you, giving you virtual applause and thumbs up.
Oh, okay.
All right. Well, everyone have a good day, and I will follow up with email of this recording as well as some other information. And until next week, we hope that you're safe and well. Enjoy yourselves.
Stay well.
It was good.
That's great.
Thank you all for attending.